Okay. Yeah, right. Joke. They're talking low densities of birds, the densities of birds in our populations. One area is 600 miles, the other area is 200 square miles, roughly. The density in the northern population is roughly 1 bird per square mile, and that is low density. Right on the slide. What is a viable population? We've been skirting around this issue. We've been skirting around the issue to a certain degree, but this is obviously a Gunnison bird, which you know by heart. Minimum viable population, there are a lot of different definitions, but here, a level at which a population can maintain genetic variability over time. It's a concept. It's a difficult number to define, but there have been some numbers presented. I've seen 50 listed as a number in which a population can maintain or can avoid problems associated with inbreeding. 500 I've seen listed as a number in which a population can avoid loss of genetic material due to genetic drift. Those two numbers I've seen fairly frequently. 500 I've seen quite a bit. And that does not necessarily mean, for example, if you want a minimum viable population of 500 birds, that you go out and count all your birds, and if you have 500 breeding age birds in the spring, you've met your goal. Because another concept that is applied to this is effective population size. An effective population size can be thought of as the number of birds that are actually successfully breeding. And that number is usually substantially lower than the minimum viable I shouldn't say it. Usually substantially lower than what you actually count there in the breeding population. And what I'm going to go through a little bit here is an attempt to describe what that is for sage grouse, and do it fairly quick. This is a greater prairie chicken, new species of sage grouse. Now this bird has been a hot topic this year. There have been papers in conservation biology and science dealing with the genetic aspects of this the population of greater prairie chickens in Illinois. It's been very interesting. Anyone who's interested in this topic, I would suggest going to those papers. The bottom line on this stuff is that what they have found is that an isolated population of prairie chickens in Illinois was losing its genetic variability, and it was quite substantial when compared with populations in Kansas, Nebraska, and Minnesota. In addition to that, it appeared to be showing up as ramifications in the population in declining fertility, which they had monitored for many, many years, and they were able to alleviate some of those problems by bringing in birds from an additional population, and that seemed to solve some of the problems. They still have the long-term problems of maintaining the population, but it's one of the few indications we've ever had that small populations can really show some substantial problems and how they might happen. In estimating effective population size, I actually went through a lot of the formulas. There are a lot of things that go into these formulas: generation length, the actual count of breeding age birds, number of chicks produced, survival of chicks, annual survival. There are other things that go into this, and they affect some of these other factors like generation length, and they have to do with breeding success. There's a lot of ideas about how many males actually breed. We use the value in our equation of 35% of the males actually had some breeding success. That's based on research in California. We don't know what the exact value is. That's a best guess. There are other factors concerning annual variation in population size. A recent paper this year in conservation biology dealt with the fluctuations in population size and how that affects your effective population size by throwing in bottlenecks periodically, and that those population fluctuations should be taken into account. Okay, this is a slide you've already seen, but roughly showing the decline in sage grouse in Washington down to roughly 1,000 birds. When we did our estimate of effective population size using conservative estimates for Washington, what we found is that the effective population size here was roughly 360 individuals. That means we were counting basically 36% of what we counted in the population, and that was a lower number than the number of males we counted. We counted 380 males in this population, and that gives you kind of an indication of how much lower effective population size might be. In any case, that was not even accounting for the fact that we have what we believe are two isolated populations. when you take those let's say, for instance, looking at northern Washington, which we did, there's no evidence, despite all these long movements, that these populations are interconnected. So what we had to do, we had to go through and treat each of these northern populations and the southern populations separately and go back and reanalyze this stuff. And you can guess what that did to our estimates of effective population size. Just over 200 in one population, just over 100 in the other population. Clearly below the level of 500, which would be recommended to avoid loss of genetic material from genetic drift. In any case, it's important, I think, too, to talk about where some of this variability is coming. We kind of alluded to the difference in mating success, big factor. There's also factors, things like annual variation in what's going on out there. This is just clutch size. And monitoring clutch size, we detected a lot of variability in clutch size. Then we get into the really tremendous variation, and this is going to be, as long as I can see, I don't need the title. But anyway, this is a percentage of females nesting. Each one of these represents a different study. We're blessed with a lot of research on this, so at least we have some ideas of where to get information. This was our study, and we're up there as far as all our females appear to be nesting. But you can see how some of the research is indicating that substantial numbers of females don't nest. That drops the effective population size down. If they're not nesting, you can automatically drop that percentage-wise from what we got. That 36% would be substantially lower. This is nest success. Here, Washington's right down here. Washington's also here, but they're different Washington studies. Washington's at 37%. Tremendous variation. Now, I won't get into the variability associated with these studies or how good they are, but the point is that the higher your nest success is, the higher the effective population size is. The same thing for re-nesting probabilities. We have a pretty unusual situation in Washington. Our birds re-nest at a very high rate. If they lose their first nest, they try again. Other places in the range are down here. There's no indication that they re-nest anything like what they did in Washington. And there's reasons for that, but the point is here that by re-nesting, they increase their potential productivity and therefore increase their population or effective population size. Because of that re-nesting, we end up with a fairly high productivity or breeding success, the percentage of females that produce a clutch in a given year, and it's fairly high in Washington when compared to other regions. Clutch size, average number of eggs is 9.1 for northern Washington. Compare that to the other areas. This is in fragmented habitat too. This goes to show you. So what do you do about it? It's a tremendous amount of variation, and that leaves us with a problem. In essence, you have to do your homework in each area and have a better feeling about what's going on in different regions. We tried to use conservative values within Washington. We underestimated what that productivity would indicate because we didn't want to overestimate our effective population size, so we tended to compromise between northern and southern Washington where we had different values because I thought it was better to be safe in that. But now that we've got that type of stuff, what options do we have? Well, first of all, we've already alluded to expanding the range by concentrating on habitat that's off on the edges of your population. This is fairly good habitat here, despite the fact that it's terribly fragmented. Another way to do it is to think about ways you can improve the habitat in there. There's a good publication that just came out this year or last year dealing with parameters of fitness and the relationship of those fitness parameters to characteristics of the habitat. Those are the types of things that can actually be applied where you can actually improve nesting success, survival of chicks, and those are the things that ultimately improve population size. They improve your populations at the same time they're improving your estimates of effective population size because you're actually affecting the underlying parameters that you use to calculate that. So it solves the problem in a sense in two different ways. Okay, the bottom line is that no matter how you look at effective population size, and I think Dr. Braun alluded to this earlier, it still comes down to intuition aspect that you basically need to manage for large populations. We don't know what the bottom line is. We don't want to be in a position, however, of watching populations go extinct in a sense of way of conducting experiments as we watch these populations go extinct, and then we can go back and look at, well, the ones that went extinct were too low. That's obviously getting this in the wrong order. We need to be in a position of having some ideas now, because we're still in a position to affect some of this stuff. So we need to be ahead of the game on this. Did I do it quick enough?
That was really great.